Welcome to the last oral presentation of today. As they call it, diamond or woman's best friend. My friend, Professor Popov, he's going to convince their scientist's best friend. So he's going to talk to us about the diamond films and nanoparticles for various energy applications. He's the director of the Center for Interdisciplinary Nanostructure, Science and Technology at the University of Kassel. We have worked together for a very long period of time. So it's my pleasure to introduce my great friend and dear colleague. Thank you, sir.
Thank you. Thank you, Professor Vasishta, for the kind introduction. Exactly 20 years we know and work together. So, good afternoon, ladies and gentlemen. So, I have the pleasure to give the last talk, the last lecture of the first day. And I would like to thank Sophia and also the organizing team for the excellent organization of the 4th edition of the International School of Advanced Materials. So today we heard excellent lectures giving one of the approaches when we are looking for materials to solve a technological problem or to improve functionalities of system or devices. Examples were given with batteries, also with photovoltaic cells. So the goal is clear, the performance should be improved. Then there are suggestions, models, simulations, synthesis, tests. So this is one of the approaches. I will show you another approach. You can look in the well-known materials, well established with also well-studied properties, and to look back to find the possibility to use such materials in order to solve your technological problem. And such material is diamond. And as Professor Vasishta said, I should convince you from the very beginning that it is possible. And I will start with an example more than 20 years old. And this is related to the preparation of the Big Bang experiments in the Large Hadron Collider at CERN. So during the initial tests of the so-called Atlas project, the leader of the team realized and published in the report, radiation in high energy physics experiments kills the silicon detectors. And why it happened? So why they had these technical problems from the very beginning? This is because the radiation damages by these high energy particles, they add energy levels in the band gap of silicon, which, as we heard in the previous lecture, is semiconductor, and they introduce these energy levels in the band gap, resulting in leakage current, in trapping of the carriers, or they create also effective doping above or below the two bands. That's why the decision was, let's look in two directions. Either to try to improve the functionalities of the silicon detectors in the pipelines, or to look for new materials to create completely new sensors and detectors. And the team with the second task proposed a material to solve the problem. And this was diamond. Why diamond? So you can see directly the comparison between diamond and silicon. First of all, you will see diamond can be also considered as a wide bandgap material. So with bandgap of 5.5 electron volts compared to 1.12 for the silicon. In addition, the mobility of the carriers, electron, but especially the mobility of holes, is much higher in diamond compared to silicon. The density of the material is larger, and as a result also the radiation hardness, so the resistivity against high energy particles is higher. And based on this, chemical vapor deposition diamond was used to create completely new sensors. You can see them there. I will explain you how they were deposited, and they were mounted in the beam lines to start this successful test performed in the Large Hadron Collider. So this was one example, old material, but solving your problem. So this is also a citation from the report. Diamonds come to help where the other materials fail. This is a good take-home message. And you will see later on with my examples. But first of all, I will introduce you the diamond films, nanoparticles, how you can synthesize diamond in a relatively inexpensive way, what are the synthesis, the growth mechanisms. After that, I will present the bulk and surface properties of diamond films with different crystallinities. And then I will give you 3 examples. Diamond as material for high sensitized solar cells, diamond nanoparticles in lubricants in windmill turbines, and diamond windows in nuclear fusion reactors. So, starting with diamond. So, for most people, as Professor Vasishta mentioned, diamond is gemstone. And people relate it with jewelry, with social events, with wealth. But for scientists, diamond is indeed a material with a number of excellent properties. First of all, diamond is the hardest known natural material. It is wear resistant with very low friction. You will see example. It's chemically inert. It is electrically isolating. I show you 5.5 electron volt is the band gap. Or the diamond, in a similar way like silicon with the same dopants, so can be doped. So to become semiconducting and with very high level of doping, even semi-metallic. You will see one example. Already the high electron hole mobility was demonstrated. It has extremely high thermal conductivity. I will pay you attention also on this point later. High radiation hardness, very broad electrochemical potential window. And last but not least, it is also biocompatible. As you see, a set of remarkable, excellent properties. What is the reason for these properties? Let's go back to the chemistry book and remind you. So diamond is allotrope of carbon, which is composed only of sp3 hybridized carbon atoms. These atoms are arranged in face-centered cubic crystal lattice. So each carbon atom is bonded to 4 other carbon atoms, and these bonds are strong, covalent, and nonpolar. So this is the reason for all these excellent properties that I showed you. And just for comparison, the second famous allotrope of carbon, this is the graphite, where all carbon atoms are in sp2 hybridization, forming these graphene layers, which are bound to each other with very weak bonds, which determine the specific properties of the graphite. So, the problem was the properties of diamond were known, but the problem was its availability. So, the gemstones or the natural diamonds are expensive and they are limited in size, also in shape. And the first breakthrough was when the first synthetic diamonds were produced. So the scientists copied the process from the nature, and they applied high pressure and high temperature, starting from graphite, adding some metals as catalysts like nickel, iron, and cobalt, and applying high pressure and high temperatures like the conditions in depth of the Earth. They were able, for the first time, to synthesize diamond from graphite. The second very important breakout was when, for the first time, much milder conditions were applied to create diamond by chemical vapor deposition, because not only the conditions were much milder, but also it was it gave the possibility to coat surfaces and objects also within diamond films. So in this case, usually the combination is methane, a source of carbon, and hydrogen. This is extremely important. I will show you why. But you can use also other carbon sources, carbon gases. Pressure, much lower. Temperatures, higher than 850, of course, much lower compared to the temperature by the high pressure, high temperature synthesis. It can be even reduced. It reflects, it's reflected, however, the reduced temperature on the quality of the diamond films. And of course, in order to activate the gas mixture, so methane and hydrogen, you need strong energy source. It can be hot filaments, so these are wires, tungsten, tantalum, which are heated to temperatures above 2000 degrees centigrade, microwave plasma, but it can be also arc discharge or laser beam. So diamond films have different crystallinity. So it means they are composed of crystallites with different sizes. And the first example, what you see there, is of polycrystalline diamond films. So composed of diamond crystallites with sizes of microns. So in this case, maybe you can see or not, the bar here, it's 10 micrometers. And what you can also see is that the surface of these films is dominated by the facets of single diamond crystals. So these facets make the film extremely rough. Some applications need rough film with larger surface. However, other applications, they need much smoother surface. And to polish diamond, the hardest known material, it's expensive, time-consuming job. That's why one of the possibilities to reduce the surface roughness is to reduce the grain size. Coming to the nanocrystalline diamond film, again the surface is dominated by the facets, however this time the scale bar is 750 nanometers. So the grains are of size 0.100 nanometers. So this reduces the surface roughness, but still they are relatively rough. Going in the same direction, we can come to the ultra nanocrystalline diamond films with crystallites up to 10 nanometers. So these films now, they don't look like typical diamond films. You don't see the facets. However, they are diamond films, as I will demonstrate you in a few minutes. So these are two examples of the chemical vapor deposition techniques used for the deposition of diamond: the microwave plasma chemical vapor deposition and hot filament chemical vapor deposition. As I already mentioned, we have similar source gases containing, for example, methane plus hydrogen. They introduce in the chamber and the gas phase is activated. In the first case by the microwave plasma, in the second by these tungsten filaments heated to temperatures above 2000 degrees centigrade. What else do we need? We need our substrates, which are placed on the holder. This holder is heated, I already told you. Above 850 is very good temperature to obtain really perfect diamond, but it can go down also. And on these substrate holders, you place the substrates. And these substrates has to be prepared. I will show you now how. And this preparation plays an important role, because all of these three types of films that I showed you, poly, nano, and ultra nanocrystalline diamond films, can be prepared by both reactor types. But you have to vary two parameters to change the crystallinity. The first one is the so-called nucleation density, which is regulated by the pretreatment of the substrate. And the second parameter is the secondary nucleation rate, which is regulated via the gas phase composition, and the substrate temperature. Starting with the first one, nucleation density. You can deposit diamond on many materials, however, not on all. The first limit is the temperature that the material has to survive. And the second is that you have to pretreat the substrate to introduce the nuclei, which will induce the growth of a closed film. Let's take, for example, silicon. If you take a silicon wafer and put in the reaction chamber and start the process, you obtain nucleation density on the order of 10 to 4 per square centimeter, or even below. So you can deposit single grains, but you cannot deposit a complete film. However, if you pretreat in ultrasonic bath your silicon wafer in a suspension containing diamond powder or diamond powders with different fractions, you can increase the nucleation density to 10 to 8, 10 to 11 per square centimeter, or even higher. What happens during this pretreatment? Diamond is hard material. It means it is harder than any substrate you want to use for the deposition. During this ultrasonic pretreatment, some of the diamond grains remain mechanically fixed. So these are IFM image. All these points there, these are diamond grains that remained on the surface of the substrate, mechanically fixed. But in addition, during this ultrasonic pretreatment, diamond grains made some scratches or network of scratches. Like you see here, again, IFM image. And also these scratches, they also serve as nuclei for the growth. And what you see here, these are in fact two diamond grains. We say it's a twin grown on such defect. So in this way, we create the defects or the nuclei for the growth. The second parameter is the so-called secondary nucleation rate. It means when we will interrupt the growth of a diamond crystal and initiate the growth of another crystal. So the higher the rate, the smaller the crystals that we obtain in the end. So this is increasing the secondary nucleation rate is the way how we can prepare these ultra nanocrystalline diamond films. Regarding the growth mechanism, it's the same for all types of diamond films, irrespective of their crystallinity. We have the carbon source, let's say methane, chain of reactions, forming radicals. It is accepted that the methyl radical, CH3, is the major film-forming species for diamond. And we need hydrogen. Without hydrogen, you cannot grow diamond. What is the role of this hydrogen? We heard in the previous lecture the problem of silicon, the dangling bonds on the surface. So they can be saturated. So in this case, this is the role of the hydrogen radicals which we have in the plasma. So when we have the bond of carbon showing to the surface not be saturated, hydrogen radical comes and stabilizes the surface. In addition, it can make a place free where the methyl radical is included. So this is the growth phase. So this is the first role of hydrogen, stabilizing the growing, but also the final diamond surface. And the second role is that these hydrogen radicals are extremely reactive. They are etching, they are removing carbon. And during this process, which I demonstrated, we deposit not only diamond, we deposit also some graphitic phase. However, the etching rate of graphitic phase with hydrogen radicals is much higher than the etching rate of diamond. So at the end, only the diamond phase survives, the graphitic phase is etched away. So that's why without hydrogen we cannot deposit diamond. So here I show you two typical deposition conditions used in my group. I want to pay your attention on the second for the deposition of ultra nanocrystalline diamond films. We have methane, 17% compared to 1, but in nitrogen. However, in this 17% methane, we have enough hydrogen to fulfill the necessary function and to enable the growth of diamond. So, coming to particles, nanodiamonds. So, under the name nanodiamonds, variety of structures are included. First of all, you can hear about nanodiamonds when, for example, the investigations of meteorites are published and presented. And what you can see here, so this is a diamond twin crystallite. Here is the one, there is the second one. They were size 2.7 nanometers. They were found in this meteorite. So meteorites contain sometimes also nanodiamonds. Nanodiamonds are also the isolated diamond particles which are deposited on the surface, or they are formed in the gas phase. In the way I mentioned, if you don't have high nucleation density, you obtain separate crystals. So this is a diamond grain, about 6 nanometers, on silicon cells. But sometimes also the nanocrystalline diamond films are called nanodiamonds. So, how they are synthesized, I mentioned already from the first group of methods, the low pressure and moderate temperature group of methods, the chemical vapor deposition, where we can prepare isolated crystals, but also nanocrystalline diamond films. There are some more exotic techniques, I will not pay attention to them. The second group is the group of high pressure and high temperatures. So the static high pressure, high temperature method was the classical one, used for preparation of synthetic diamond. However, in the later years, two more modifications were established. The so-called shockwave transformation. Here we have static application of pressure. In the first case, then we have, by the shockwave, very fast application of pressure. And another technique is the so-called explosive condensation. So these are the so-called explosive diamonds. For example, each explosive, when it is ignited and after the explosion, gives also some nanodiamonds, together with many other carbon modifications, of course. And the third group of methods are the so-called irradiation-assisted methods, the application of electron beam with mega electron volt energy, so heavier ion beams like neon or krypton, or application of laser beam. So these are the techniques that can be used to prepare nanodiamonds. So here a very brief overview about the possibilities regulating the nucleation density and the secondary nucleation rate. You see the single or separate diamond crystallites by low nucleation density, and you see the closed uniform diamond films. Of course, we can vary the crystallinity here. So, increasing the secondary nucleation rate, we are coming to the ultra nanocrystalline diamond films, and there you see example also by variation of the nucleation density, single, balls, so these are not single crystal diamond. So these are balls which are composed of some diamond crystallites. I will show you in details the properties of the ultra nanocrystalline diamond film, up to closed ultra nanocrystalline diamond film on silicon. So, about the properties. to be able to differentiate the properties of the nanocrystalline and ultra-nanocrystalline diamond film. The nanocrystalline diamond films, the crystallites, as I said, of several hundred nanometers, they start the growth from the interface, from the nuclei created during the pretreatment upwards. The longer we deposit, the thicker the film, and the higher or larger the crystals. By the ultra-nanocrystalline diamond film, we have extremely high secondary nucleation rate. It means we interrupt the growth of diamond and start the growth of new diamond grain. And as a result, we have diamond nanocrystallites up to 10 nanometers, and they are embedded in amorphous carbon matrix. We have also very small amorphous carbon matrix or amorphous carbon on the grain boundaries between the individual diamond grains, but because the fraction of crystalline phase is so large, for many things it can be neglected. However, by the ultra-nanocrystalline diamond films, this amorphous phase plays also an important role. The characterization shows the differences, for example, by X-ray diffraction, ultra-nanocrystalline diamond films show much broader diffractions. This is the effect of the crystallite size. By Raman spectroscopy, we can observe the diamond characteristic peak by the nanocrystalline diamond, but not by the ultra-nanocrystalline diamond. This is because of the masking from the amorphous phase. So the Raman spectroscopy is much more sensitive to the amorphous than to the crystalline phase. So the same differences are observed, for example, in electron diffraction. So here we see two grains from the nanocrystalline diamond film, so the grain boundary, and characterizing only on one of the grain, you see the monocrystalline phase of diamond. By the ultra-nanocrystalline diamond, they are differently oriented. That's why you see these concentrated rings from the selected electron diffraction. And this is electron energy loss spectroscopy mapping of one diamond grain. And for each pixel, the spectrum was compared to spectrum of diamond or graphite. And the software decides which phase do we have. And you see very well, this is the grain of diamond surrounded by amorphous carbon. So this is the spectroscopy used, so electron energy loss spectroscopy, and in fact you can see very well the difference between diamond and graphite, the presence of the pi star contribution related to sp2 bonded carbon atom, its absence by the diamond phase. The surface I already demonstrated, the surface of the nanocrystalline diamond films dominated by the facets of single grains. The films are closed, uniform, and they are large. As I already mentioned, sometimes it's good, sometimes not. Depends on the applications. In the case of the ultra-nanocrystalline diamond film, the surface is much smoother. So this is measured by atomic force microscopy, showing lower surface roughness, and you see some rounded features in atom. So this is due to the growth mechanism. Nuclear, we start the growth, then we interrupt the growth, few more nuclei are created, and that's why it forms something like cauliflower structure. And one argument that each diamond film is hydrogen terminated, this is the study of the hydrogen depth profile by nuclear reaction analysis, showing the decrease of the nitrogen towards the surface, reaching about 13-14 atomic percent, but also the amorphous phase in the, let's say, composite material UNCD also contains about 7.58 atomic percent hydrogen. The surface hydrogen makes the diamond surface stable, which is very good. However, sometimes we need some additional functionalities on the surface. So the hydrogen terminated surface, in this case UNCD, is hydrophobic, contact angle 75-85 degrees against deionized water. This stable surface can be changed applying highly energetic processes, either plasma or photochemical. And, for example, applying oxygen plasma or UV ozone treatment, we can change the termination from hydrogen to oxygen. It's oxygen, but there are different groups containing oxygen on the surface. If we apply ammonia plasma, we obtain amino terminated, so some amino groups on the surface. In both cases, we come to highly hydrophilic surfaces with contact angles below 10 degrees. In the opposite case, if we use fluorine containing plasma, for example, sulfur, fluoride, trifluoromethane, we obtain strongly hydrophobic character. So with contact angles higher than 110 degrees centigrade. So these modifications are accompanied by exchange of the surface termination, and this is proven by X-ray photoelectron spectroscopy, showing, for example, by UV ozone the increase of oxygen, even higher by oxygen plasma. With ammonia plasma, we have mixed effect. This is nitrogen, this is oxygen, because of the rest water. So it's a kind of a mixed termination. In case of fluorine modification, so fluorine is the green one. You see after only 5 seconds, trifluoromethane going above 20%, which increased just a little bit after 5 minutes. Also in case of sulfur hexafluoride, we have increase, of course, of the fluorine surface concentration. Here the comparison is with Teflon, just as a reference for the characterization. So the change of the surface composition after modification is in fact the replacement of surface hydrogen termination. So let's start with the examples. The first example is diamond as material for dye-sensitized solar cells. A little bit crazy idea, but we wanted to try with colleagues from 2 other groups, from electrochemistry and metal-organic chemistry, and my group. This was about, maybe 15 years ago. We started with the idea from boron-doped diamond, which was used as electrodes for some advanced applications for purification of water. I don't remember exactly. But this motivated us. And we could obtain very high dopant level in the lower 10 to 21 per cubic centimeter range. So it's very high doping level, which gives almost metallic conductivity of diamond. I mentioned already it has very wide electrochemical potential window, so between the reduction and oxidation points, it is a really large area. The high stability, which is high irrespective of the pH conditions, acids, bases, it's not affected at all. And the possibilities for surface modifications, if necessary. And this is necessary because what we heard in the previous lectures about such solar cells, we need absorption. The photons, sunlight, but it cannot happen with diamond. It's transparent. It's transparent. That's why it will not work. in order to make it working, we need something else that can absorb the sunlight. And this could be dye molecules. So this is the sensitization of the electrode with dye molecules that absorb the sunlight, creating electrons. And our metal-organic partners said, let's think about something which is similar to chlorophyll. Let's also resemble in this way how the nature is doing this. So then we started this a little bit crazy project. What I'm showing here, this is what you observed in the previous lecture. These energy levels, we have to make these stairs providing, of course, in the previous lecture, what was demonstrated, this is experience from many, many groups, I don't know how many, for many, many years. When we started, there was almost no any input. Yeah. So, what we have to match? We have to match the complete system. We have diamond, yes. Depending on the level of doping, it's fine. However, the surface termination of diamond bends the edges of the valence and conduction band, which is important for the contact with the dye molecule. Dye molecule, it has also two extremely important parameters, and this is the electronic structure. The highest occupied molecular orbital and the lowest unoccupied, which is important for the absorption and for these steps transferring electrons or holes. So we started as enthusiasts looking for such dye molecules as light harvesters and electron donors. So the colleagues in chemistry, they made some calculations because, first of all, we varied the surface termination because it changes the bending of the edges. They started quantum chemical calculations of different phthalocyanide. They decided to use different phthalocyanide molecules to calculate the electronic structure. So we started. Of course, to provide this flow of electrons, we need attachment of the dye molecule on the surface. Also in this case, previously I showed you about the ultra nanocrystalline diamond. This is the case of the nanocrystalline diamond. We can also modify it with oxygen plasma, changing the wettability and providing some oxygen species on the surface, which are important for the grafting of the dye molecules. So these are the first molecules that we tried. Phthalocyanines containing a central element manganese, copper or titanium, also with different side chains. And after the modification of the diamond electrodes, or boron-doped diamond, they were exposed to phthalocyanines, solution 1 micromolar in dichloromethane for 12 hours, followed by a thorough ultrasonic cleaning in the solvent to remove all non-covalently bonded molecules. And we characterized by XPS, and we found that we have molecules on the surface. By the titanium phthalocyanide, we detected here other compositions. So the titanium phthalocyanide was the only one containing sulfur in the side chains. We detected titanium, sulfur, also nitrogen, almost in the same ratios as in the phthalocyanide molecules. In the copper, the presence of copper with ratio 1:8 compared to nitrogen, presence of manganese, also slightly increasing of the oxygen content due to the oxygen in the side chains of the manganese and copper. So just to, this is 0.6%, of course, very low, what can be also expected. So with this manganese, titanium, copper, with different terminations and modifications. We started first experiments. We prepared electrodes, diamond working electrodes, isolating it, opening just one hole here for the contact. And as counter electrode, we used platinum. Also, we used reference electrodes. We performed a lot of measurements. So here you can see, for example, cyclic voltagrams of electrodes. In this case, with manganese, tungsten, in darkness, but also upon illumination with light, 770 nanometers. You see after different modifications how the cyclic voltagrams were looking like. And we used also, starting with different electrolytes, and what you can see here, for example, measurement of the current upon switching on and off the light. And also these signals, they appear with very good short response times within 2 seconds. So after a few years work, we said probably now we have our first experiments to apply for financing, but we never received it. They said when you can demonstrate, I think at that time the efficiency of silicon was above 10 for sure. In our case it was below 1. They said when you can reach the standard silicon at the moment, you can expect financing. And unfortunately we gave up. However, the idea works, and as you mentioned, of course, 3.5 can have some special applications. You never know. Everything is developing, and sometimes people are coming to old solutions. The second example is diamond nanoparticles in lubricants for windmill turbines. You said diamond as lubricant. So again, I'm starting with example to convince you, and this is example from my group. So we took ultra nanocrystalline diamond films, and for the wear tests, tribological tests, we used monocrystalline diamond ball. It was extremely expensive, 3 millimeters, sorry. Sliding. Applying different forces of 2 nanometers and 10 nanometers. And you can see the images of the white light interferometer. You see nothing after 100 cycles. Nothing. Of course, with higher pressure, 10 nanometers, you see some wear of the UNCD film. But what is more important, the recording of the coefficient of friction. You see, these are 2 different samples. With 2 nanometers, 2 newtons, we obtain about 0.02. Probably you don't have the numbers in mind. However, when you speak about frictionless systems, people say Teflon against Teflon. Teflon against Teflon has friction coefficient of 0.04. Diamond against diamond is 0.02. So it is approaching frictionless surfaces. So I think I convince you that they can be used as lubricants. Of course, not in the form of layers. This will make everything very expensive. If you cover all these steel parts, first you cannot cover with diamond, it's another story, but it's expensive. However, it is a trend to improve the properties of lubricants by additives. This can be nanoparticles, but also organic friction modifiers, also some inorganic substances. So this brings additional potential in friction and wear reduction. And the reason is the formation of tribofilms that prevent the direct contact between the sliding surfaces. And one example is the application of nanodiamonds. So we have here additives in the main oil. This is polyalpha-olein oil. We have also additional additive. So, but let me say how it works without going into detail. So, diamond grains are, or nanoparticles are modified, their surface. They start to interact with the other additive. They're encapsulated in the course of the process. So this is a diamond, they're encapsulated, and then they form this tribofilm on the surface of the steel part in the turbine. And in this way, this synergy is achieved between the diamond nanoparticles and the organic modifiers to form such novel, environmentally friendly lubricant which has advanced geological properties. So this is a citation not from our group. I don't show the results. They obtained coefficient of friction of about 0.04. So something similar to polytetrafluoride into Teflon. And very fast, because the time is running, the last example. Diamond windows in nuclear fusion reactors. Sounds also strange, yes? So, you know, nuclear fusion is one hope, one expectation as energy source. What is in fact nuclear fusion? This is the process or interaction of two very light atomic nuclei. For example, deuterium and tritium, two isotopes of hydrogen. They react, fuse together, they form heavier nuclei of, for example, helium, and they leave extreme, enormous amount of energy. So this is the nuclear fusion. So nuclear fusion reactors are extremely complex. So this is only part to show you, for example, this donut shape device, which is designed to confine reactants, for example, deuterium and tritium, in very strong magnetic fields and under extreme conditions. So, very complex magnetic, electrical fields, plasma. This is, let's say, the heart of the nuclear fusion reactor. It looks much more complex. However, where is the role of diamond? So, these nuclear fusion power plants require electron cyclotron heating and current drive systems for the plasma heating and stabilization. So microwave plasma beams, so high power, 1 to 2 megawatt, are generated by gyrotrons, and they propagate along the waveguide transmission system to special parts where they have to locate the reactants. And the key component in such transmission system are CVD diamond windows, because diamond is the only material that fulfill all requirements. First, it has to be transparent, highly transparent. Second, it should be highly thermal conductivity. Third, it should confine, so the vacuum conditions, but also to isolate hazardous materials. Also, there are some radioactive dust from the rest of the systems. And such windows are made of polycrystalline diamond in the similar way, similar films, which are demonstrated. In the conventional configuration, there is one disc, I will show you, perpendicular to the beam propagation direction. The thickness is important. The thickness of the beam of the window, diamond window, should match half of the beam wavelength. So these are microwaves, so it should be the order of micrometers, in order to minimize the amount of reflected power from the disc. I said optical properties. Diamond is transparent material from the ultraviolet, so this is the band edge, to the far infrared. When we speak about the applied here microwaves, they're even behind. The only absorption which is observed, this is the range 2.5, 5.6 due to 2 and 3 photon absorption. Absolutely transparent. That's why it is an ideal material for multispectral optical application, also in the fusion reaction systems. Thermal properties. Comparison of diamond to metals. And this is the most prominent thermal conductor, copper. What you see, diamond is 5 times better than copper. What is the reason? The reason is that by all these metals, so steel, titanium, copper, aluminum, the thermal conductivity is realized by electrons. By diamond, the thermal conductivity is realized by phonons, the vibrations of the diamond lattice. And as I mentioned, diamond possesses the most dense lattice possible. That's why these phonon vibrations are so effective to conduct the thermal energy. And in addition, diamond has very low thermal expansion coefficient, which makes an excellent material for any thermal management applications. Not only in this case fusion reactors, but also submounts for high power integrated circuits, laser diodes, etc. So this is just one part of example, the nuclear fusion reactor, which is built in France, type tokamak. You see the girons, you see the torus part of the system, and here is diamond needle, which is mounted together with this metal parts and should provide all these specifications, be transparent, isolate the system from radiative particles, but provide high thermal conductivity, etc. So with this, I'm coming to the end of my lecture. I presented you the wonder material called diamond, not only girls' best friend, as Professor Vasishta said, but also scientists' best friend due to the set of excellent material properties. I showed you the methods for synthesis of films and nanoparticles, and also the characterization of the surface and bulk properties. And I gave you a few examples, some strange maybe at the first sight, but some possible. That's why, don't forget, sometimes diamond comes to help where all other materials fail. So thank you for your attention.
All right. So presentation is now open for questions. Let's see if there are any questions. Yes, sir.
Just have, thank you very much for this presentation. Just have one question about UNCD fields. Do you have any idea about its adhesion? That's the most important
Adhesion.
adhesion.
So adhesion I didn't mention because it's a complex topic. Adhesion is good on substrates which can form a monolayer or few monolayers of carbide. Titanium, for example, is very good substrate, but not steel. So that's why not the crystallinity is important, but the surface or the material of the substrate. This is important.
Yeah.
Otherwise, they have good adhesion properties on substrates like silicon, like titanium. We have coated implants for biomedical applications with titanium. So the adhesion of UNCD is good, although that not each crystal has contact with the surface. The adhesion is good.
Because when you say we have a low coefficient of friction, it's a good thing. But if we have to die, so we can't use it. So just ask for the area that we can use this field.
The adhesion is also good. believe me, the adhesion is good. We performed complete mechanical study. So also hardness, friction, physiological properties, adhesion, everything was studied in a complex investigation regarding some, the same way, coating of implants, especially where they have this movement, they are not static. So the adhesion is good.
Any more questions? Yes, sir.
Thank you, dear professor, for your presentation. I want to just ask you about the process of the synthesis, more precisely about the deposition condition. So how you choose them, and what do you think about like including the modelization in the process? Like before proceeding with the experiment, like you can do modelization to test, let's say, minimal conditions. They are satisfied, and then you can do the experiment.
The choice of conditions, first of all, they are determined once by the substrate. So the substrate should survive the heating. So there are some publications, I don't believe them so much, but they deposit diamond also on plastic foil. So for me, when I started working with diamond 26 years ago, at my first diamond conference, a professor from USA said, young man, you are new here. I said, yes. When you started working with diamond? I said, a few months ago. He said, I will give you something from me to remind you of me and of diamond. And he gave me a sticker with dragon with fire coming out of the mouth of the dragon, and there was a diamond formed. So you need power to form diamond, you need temperature, you need high activation. That's why you need to select parameters according to the substrate. It is possible to find also glasses. We have deposited diamond, ultra-nanocrystalline diamond on glasses, but they're special. They have glass temperatures a little bit, let's say 30, 40 degrees higher than the temperature we had used. So this is the first. The second is depending on the quality. If you want to use, let's say, ultra nanocrystalline diamond, which we can say low quality regarding crystallinity, we can reduce the temperature, we can increase the methane concentration, we can exchange partially or even completely hydrogen with nitrogen. So this is the selection. What can be modeled? So in fact, there are not so many things because the processes are clear. You have this chain chemical reactions, leaving one by one the hydrogen atoms in the molecule, giving radicals until you come to C radicals. But experiments, optical emission spectroscopy, if I remember correctly, was used to study in situ the species in the gas phase, how they change their concentration during the process, the initial start stage, the final stage of deposition, and that's why they consider that the methyl radicals plays the most important role. Not CH2 or CH or even C, but so. What kind of models can be performed? I have never made any, to be honest, because I was following, so diamond was in the beginning of the 90s, in the last century, there was a boom. So diamond could be synthesized, diamond can be coated on so many things. So also theoretical works were published at that time. So that's why I don't think there is much to do on this part, on the theory.
So there may be another explanation for dragon with the flame.
Yeah.
Because I used to make diamond using acetylene torch.
Yes.
Exactly. That makes perfect diamond, by the way. So that may be the significance.
Acetylene torch, but as a source of power.
Exactly, the source power. Sure.
I tried to use this gas mixture. It was catastrophe, but it's enough.
No additional questions? There's one more
Yeah,
question.
no, just, yeah, you mentioned that you use diamond for lubricant. I'm just wondering about the scalability of the easiest, about the quantities and also the surfaces that you can coat. And that's it's a huge problem, especially if you want to do that for into wine.
Yes. In fact, it's not. The companies are keeping this secret. So you cannot, yes, you cannot find. They just write some commercial names of some additives. What is behind, you never know. This accountant publication, it was not mentioned, many things were not clear, but the idea is clear. Diamond particles are modified, they form triple film on the steel surface, on both of them. And they prevent so this is, I want just to show the details, I cannot even
But people like this photograph, whether it's Adobe Photoshop or AI.
No.
But it's all
Madame Tissot, maybe.
In London, yes.
Yeah, I guess it.
all right. Let's thank Professor Popov.